So, dear colleagues, good afternoon. I hope that everything is okay with my connection and you hear me and you see me. It's really important for me, for us. So I'm glad to see you as a participants during my lecture. As you can see on the slide, my lecture connected with the challenges and applications of artificial light sources for horticulture applications. So first of all, I would like to say several words about myself. My name is Damir Valiyev. I am associate professor in the School of Advanced Manufacturing Technologies, Division for Material Science, Tomskого University. I defended my PhD thesis 8 years ago in the solid state physics. My research interest connected with, in general, with luminescent materials, especially with the phosphors for LEDs, ceramics, some glass materials, and something like that. On the right side, you can see that some briefly depicted scientific direction which realized in optical engineering direction in my school. In this case, you can see the laser technology, lighting engineering, optical materials, and of course, agro-biophotonics. So my task today, give you a short review about artificial light sources. According to this, I divided my presentation into several parts. Firstly, I will briefly consider the issues connected with the light and electromagnetic spectrum. General terms and metrics also will be considered for separation light for plants and for human especially. So the next we will discuss with you the information about artificial light sources for horticulture applications. Especially we consider it such as legacy group of light sources like incandescent and gas discharge lamps and modern light sources like LED lamps and so on. And at the end of my presentation, and I will show you in detail some practical examples how we can apply LEDs as a modern light sources for horticulture application. So first of all, I would like to consider the light. So what is light? Light is one of the most essential requirements for the existence of living organisms on the Earth. At present, the sun is the most powerful source of natural light that is available on the Earth. As usual, visible sunlight appears white for us due to the mixing of wavelengths perceived by human eyes. So I suppose that all of you think and all of you see that the prism can decompose the white light into several components. The sun also emit gamma rays, X-rays, and radio waves at various intensities. So we perceive the portion of small part of energy using our eyes, which called the visible light. What is visible light? In general, we can see that it's electromagnetic radiation that is visible to the human eye. It's measured in frequencies or wavelengths. There are a lot of variants how we can calculate it using some very famous formula. Furthermore, light is defined as a particle called the photons. All of you, I think that you know this term. As usual, visible light range from 308 nanometers, especially with the high energy photons, to 718 nanometers. As usually, red light, with a little bit low energy photons. Light has triggered the cycle of the ecosystem that enabled plants to synthesize their food and also provide food for other living organisms in the environment. Plants and some other living organisms, including bacteria, need light for photosynthesis. So, if we speak about plants, we should use the photosynthetically active radiation terminology. There are a lot of them, and what does it mean? The PRR ranges approximately. It's about the spectral region from the 400 nanometers to the 700 nanometers. The various wavelengths in sunlight are not all used equally in photosynthesis. Plants contain in general several pigments that absorb specific wavelengths of light while reflecting others. The most important pigments in photosynthesis are chlorophyll A and chlorophyll B. All of them absorb wavelengths in the blue region and also in the red region. Especially there are some diapason and spectral region is located depicted in the picture. So also beta carotenoids can be considered for the further discussion. So natural sunlight is the cheapest source of light available, but it's not always attainable in sufficient quantities every nook and corner of the world. Consequently, farmers started relying on the artificial light sources for cultivating plants in gloomy, misty, or overcast conditions. The rising human population has led to mounting food demands and thereby need for expansion in the agricultural productivity. In general, indoor farming is not affected by the weather condition. For example, floods or droughts, maybe something other, what happens with us. It also assures availability of uninterrupted food supply all around the year to quench the demands of the rising population. This type of vertical farming makes use of artificial light sources as grow lights for the crops to carry out photosynthesis in the absence of natural sunlight. There are at least three main purposes for using artificial light sources in horticulture production. I select the first purpose is the replacement of solar radiation into completely artificial environments in order to control optimally all environmental factors and, of course, to improve quality parameters. Next one connected with the issues of adaptive lighting when the solar radiation levels does not enough for plants. And finally, photoperiodic lighting is used to stimulate or influence photoperiod dependent plant responses. It's especially important for flowering or vegetative process when we speak about the photoperiodic lighting. Of course, the use of artificial lighting is not just limited to indoor farming, but its application has also been extended to several greenhouses as supplementary light source when sunlight is not available in the desired intensity. Particularly in the winter, artificial grow lights come to the rescue as the sun does not shine bright enough for the crop plants to gain adequate light for carry out photosynthesis. Let's briefly consider the most spread artificial light sources which used for horticulture application. So, what we would like to say? I say that artificial lighting technology began 10,000 years ago and continues to be refined even today. The prehistory lighting started from a torch of fire, and with the advent of time, substantial progress was accomplished in the field of lighting technology. With the discovery of electromagnetism and electric current in early 19th century, many scientists attempt to devise a simple and affordable electrically powered home lighting. The outcome of the efforts made by numerous scientists led to the invention of incandescent light bulb, one of the greatest inventions of mankind. So there are several questions that appear. So how all these light sources work and what the advantages and drawbacks all of them. Using the next slides, I will try to answer on this question. So the light sources, artificial light sources, can be classified into three generations on the basis of the working principles. We know there are three major light source technologies: incandescence, when we speak about the incandescent lamp, electrical discharge, it's in general fluorescent and high intensity discharge lamp, and solid state lighting, like very famous LEDs, light emitting diodes, and also organic LEDs. The first two are known as legacy technologies, and the third is considered as modern technologies. The most relevant types of lamp in horticulture are incandescent, low pressure sodium, high pressure discharge lamp, and light emitting diodes. Despite the technical progress in light technology, no light source converts electrical energy into light. All light sources also produce thermal energy. Hence, waste heat increases the production cost. Therefore, in general, when evaluating artificial light sources, several factors should be taken into account, like lamp efficiency, intensity, spectral quality, cost, electrical requirements, maintenance demand, and as usual, lifespan. It's also really important parameters when we speak about the artificial light sources. Thermal radiation can cause heat stress during hot periods. Due to this reason, a suitable type of lamp has to be determined for each individual application purpose. In order to choose the best light source for plant growth, it's necessary to understand the principle of operation, characteristics, and applicability of typical light sources. Let's briefly consider the different type of incoherent light sources separately. So, the first very successful electrical light source is the incandescent lamp. It's really famous. So, it's around for about more 150 years. They played a major role in electrification of many countries. So today, incandescent lamp produce light by the electrical heating of metal wire. This type of wire can be used as a tungsten filament. These filaments, when the electrical current through this filament transform heat into emission in the visible part of the spectrum. The metal wire is mounted in a glass bulb filled with an inert gas. According to the Planck law, the filament must be heated up to 2400 Kelvin for white emission color. Unfortunately, only around 6% of their energy is radiated in the photosynthetically active radiation spectrum. 82% is emitted in the infrared, with the remaining just only 12 as a thermal energy. Although they are not very efficient with respect to delivering light for photosynthesis, they are still useful for manipulating photoperiodic signaling. For example, night break and long day light, especially for the plants, since they produce large amounts of red and infrared region. Incandescent lamps are now gradually being phased out due to the rather low light generation efficiency. Alternative way in this case applied halogen lamps, with efficacies up to some 20 lumens per watt. Halogen lamp contain a halogen, like for example iodine, bromine, chlorine, and something like that, and to the normal gas filling. The combination allows to increase the lifetime of the lamp due to halogen cycle. As usual, this type of lamp used in the compact reflectors. Incandescent lights generate a lot of heat and should be placed farther away from the plant foliage. As usual, experimentally supported that the distance between the plant and incandescent lamp should be 24 inches from the plants. In any case, incandescent lights are better used on flowering plants. Also, it can be used to prolong the short days during autumn, winter, or spring. While the initial expenditure to purchase incandescent bulb is very cheap, they are much costlier to operate when compared with other grow lights. So, the next and the second group of the gas discharge lamp consists of the artificial light source based on another, maybe principle and other technologies. There are three main types of gas discharge lamps we know. As usually really famous fluorescent tube, especially low pressure mercury lamp, mercury vapor, and metal halide lamps. I will also separately can be highlighted the sodium lamp, really famous in agricultural questions. All of them use phosphors excited by electrons to create light. Metal halide lamp and high pressure sodium lamp are the typical of high intensity discharge lamp. They will be mainly introduced in the next slides. In the presentation, I will focus only to the mercury-based technology lamp. So, the next revolution in lighting was marked by the invention of the fluorescent lamp. The first commercial available product was invented by General Electric in 1936. Initially, this concept was thought to be very suitable for colored advertisement lamps. FLs may be divided into two classes. The first one is tubular form, and the next one compact. Just the difference connected with their shape and sizes. Also, the luminous efficacies or two designs differed significantly. The working principle for both types of fluorescent lamp essentially the same. Both of them consist of arced hollow glass tube. In this tube, without some, fill it with a mixture and argon vapors in a low pressure environment. The low pressure mercury vapor discharge lamp produce visible light due to fluorescent or phosphor coating. The fluorescence appear when the excited electron hits the mercury atoms that generate the ultraviolet emission. So in general, ultraviolet emission excites the phosphors and visible light is released. Since the emission spectrum of photoluminescent entirely depends upon the phosphor coating. A wide variety of phosphor, so we know today, and all of them used for developing white and colored fluorescent lamp. So the main losses in a fluorescent occur in the ballast, which supplies a pulse of high voltage to initiate the discharge. Difference in the main principle compared with incandescent lamp sources. So, however, a significantly higher amount of energy is lost during the conversion of ultraviolet rays into visible light, where almost half the energy of each photons is lost as heat. Approximately 19% of the photons emitted are in the photosynthetically active radiation region. However, spectral output of this type of lamp cannot be regulated. This lamp puts out very little heat, which allows them to be hung close to the plants. It's very affordable and convenient for use. These are quite popular for propagation, early vegetative growth, and overwintering semi-hardy and tender plants. As usual, T5 and T8 fluorescent lamps are the most modern type. And so it's commercial available as a single or maybe day-shinable strips or maybe in the panel arrays, as you can see on the slide. A fluorescent grow light's electronic ballast does not emit noise or vibration. A smaller version of the fluorescent tube are compact fluorescent lamps. So the principle is working just the same, but if we try to use it for the plant illumination, we should put it directly into some reflectors and then use it for the illumination of the plants. So, however, fluorescent tube makes use of highly pressurized mercury vapor and neon, argon, krypton, xenon gases with the tube. This can provide hazardous to environment if not disposed of safety. So the next type of lamp in this family is mercury vapor lamp. So we can call it another one as a high intensity gas discharge lamp. So this type of lamp also work using the arc through the vaporized mercury in a high pressure. So compared with the previous one, we use the low pressure gas into the tube. In this one, we use the high pressure. So this allowed us to create very bright light directly. The arc discharge lamp is generally confined to a small fused quartz arc tube mounted within a large glass bulb made of borosilicate. There are two types, namely high pressure and low pressure. Of course, we can separate it. In low pressure mercury vapor lamp, glow is absorbed when electricity is passed through liquid mercury. The next, liquid liquid mercury connected with the electron, with the fast electron, and it's allowed two electrons go to some more excited states and release it with some portion of energy. like we see as usual some portion of energy in ultraviolet spectral region, and this ultraviolet excited the phosphors, and is usually the phosphors have a luminescent process. So, and we can see that some white emission. This lamp starts with a small arc between the starting electrode and the main electrons. So if we speak about the efficiency, so it means that this type of lamp is more efficient than incandescent, and with luminous efficacies of about from 300, maybe not 300, sorry, 35 and 65 lumen per watts. Their lifetime is range about 20,000 hours with a high intensity and clear white light output. So how we can use it for the plants? Although the initial cost of setting up the high intensity discharge grow light seems affordable for plant growers, the initial saving gets overshadowed by the additional cost that cannot be avoided. So this type of lamps create light by passing an electric current through the metal vapor. They charge the electron and cause them to bump into each other. So on the other hand, if we see and if we use it especially for the plant growing in any stage of light, but it will come at cost and they require a great deal of attention. So of course there are hazardous liquids, mercury, some a little bit limited this type of lamp for practical application, especially in horticulture questions. So metal highlight lamp is a modified version of high pressure mercury vapor discharge lamp. So inclusions of metal highlights along with the mercury vapor and inert gas permit the optimization of the spectral quality of the emitted radiation. So metals such as sodium, scandium, indium, thallium, and dysprosium are used in this type of lamp due to their characteristic emission spectra in the visible range. Generally, iodides and sometimes bromides of this metal are chosen because they are easier to vaporize and ionize than the pure metal as such. Like other HID lamps, the same mechanism of operation is followed for electron excitation and light emission. However, the outer casing is made of ultraviolet filter in quartz glass to block the ultraviolet radiation of mercury. Since the light emitted by the lamp is a mixture of the radiation by the individual metals present in the vapor mixture changing, the combination of metals highlights allow the produce of metal highlights lamp with the various emission spectrum. It's really important because it allowed us to practically change the color of the emission spectrum of this type of lamp. So if we speak about the efficacy, so it means that efficacy a little bit higher, so about 100. And sometimes in literature, I have found the information about that the limit of the efficacy for 120 lumen per watt. So they are also can be used for plant growing, and so especially the energy efficiency of approximately 25%, maybe sometimes is not usable, but not usable due to the several regions, several reasons. Because blue light promotes plant growth and excellent for green leafy growth and keeping plants compact. They also contain some ultraviolet, high intensity ultraviolet emission. In general, it's useful for combining pests and molds and promoting the production of essential in aromatic crops. It's the best type of light to be used as a primary light source when the scarcity of natural sunlight is felt. Also, the bulb will continue to light up even after its average lifespan of 2000 cumulative hours. It's not worth to use beyond the span due to the gradual decline of light intensity. So the next type, and maybe more spreadable, especially for greenhouses. It's high pressure sodium lamps. So this type of lamp, greater coverage of the visible spectrum than mercury vapor lamps. So the main reason of that, this type of lamp contain the sodium vapors along with the mercury in the arc tube. Further, the tube is pressurized with xenon instead of argon. The vapors are maintained with a ceramic of, or maybe polycrystalline aluminium tube, which can withstand the corrosive nature of sodium vapors at high temperature and pressure. The excitation of mercury and sodium atoms occurs by the bombardment of electrons from the tungsten electrodes. The electron impact ionization coupled with the thermal ionization results in electronic jumping to various higher energy states. So it means that after this process, the electrons relax to the ground state, and after that, electrons emit electromagnetic radiations. So this radiation covering a wide spectral range, especially in the visible light, in the visible spectrum. So HPS lamp have made them a popular source of electrical lighting in the public spaces and industrial building. So as usual, as you can see on the picture, in general, the high emission peak in the green-yellow range render as a distinct yellow coloration. Further, the unbalanced spectral quality in relation to the absorption peak of the chlorophyll A, B, and maybe beta-carotene makes them unsuitable for promoting photosynthesis and photomorphogenesis. Previously, I said that all of these pigments absorb light in especially blue and the red part of spectral region. HPS lamps with the high electrical efficiencies of about 30% are the most energy efficient light source used in the cloud burn. So, although they are not the best at present. So, why? Why is the reason is that? So, because the lighting system are more efficient than several others in the past. They usually emit an orange light that is incredibly bright, powerful, as you can see on the picture. So, in general, unfortunately, for the plant growers, the light require a lot of power to run effectively and produce a large amount of heat, especially in addition to hazardous level of carbon dioxide emission. So in comparison, LED lighting has the ability to make use of more effective wavelengths that actually provide benefits to plants. Let's talk about LEDs. So we can practically go to the LEDs because the LEDs maybe nowadays as an alternative way, if we speak about the more efficient, more tunable color spectrum for the plant growth issues. So the next revolution in lighting is now going on. Inorganic and organic LEDs operate at low voltage, generate light by a recombination of electron and holes. So this happens in semiconductor materials. So LEDs in general looks like a device that emit lights upon the flow of electricity, following the principle of electroluminescence. In solid-state lamps, the electric current is converted into light by a recombination of excited states of atoms into the ground state via emission of the photons. Material science in this case play a vital role because when we change the semiconductor materials, we can opportunity to change the emission spectra of LEDs. You can see there are a lot of emission based on this type of materials. I mean the semiconductor materials. Modern LEDs are available in the broadband wavelength across from the ultraviolet to the infrared spectral region, which have been becoming popular due to the high efficiency and brightness. So nowadays, LEDs are used in anywhere, such as indicators and signs, LCD backlights, displays, indoor and outdoor lighting, traffic lights, greenhouses, lighting, and so on. So it's really popular. maybe it's real popular that it's allowed to integrate it, this small or maybe teeny LED chip into the board and realize a combination of different spectral region emission. So according to this, in a really brilliant event in 2014, because the group of Japan scientists were honored Nobel Prize in Physics for the development of efficient blue light emitting diodes that in general allow to produce white light for lighting purposes. I said previously, the application of LED is really famous, it's really spreadable in our life. So how we can create the white light? So using the LED especially, or maybe some other approach, of course we can take some filters, yeah. For example, if we have the white light sources, put the filters and cut it from the white light, some due to the absorption process, some colors which you needed. So especially there are other types. If we speak about the LEDs, we can produce for example, free or maybe tetrachromatic LEDs like blue, red, and green colors. Mix it together, and finally we receive the white light. So, as usual, such LEDs are called trichromatic. It's also depend upon the combination of monochromatic LED use. So there is another approach. We can use the phosphor-coated blue and ultraviolet LEDs are the preferred source of white light owing to their common availability at low cost. However, the initial phosphor-coated LED models suffered from the significant energy losses at the phosphor due to low energy conversion efficiency. So it means that we have some dramatically, the efficiency a little bit decreases. Approaches are being made to develop a high efficacy white LED using a hybrid model, which includes colored phosphor and one of the monochromatic LED. So in general, a decrease in total internal refraction with the chip and device encapsulation with a multicolor emitting phosphor could enhance the luminous efficiency. So I said when I described the principle of operation LED, there's some terminology like electroluminescence. So if we speak about the white emission or maybe some radiation, we should to use, especially using the phosphor, we should to using some really important phenomena like luminescence. The photoluminescent phosphor materials nowadays are extremely important source of light to fulfill the technological demand over the conventional light source for eco-friendly environment. Phosphorus in general, it's a powder inorganic materials. As usual, it's the mixtures of the different type of oxides. Most spreadable today phosphor, it's really investigated material is yttrium aluminum garnet doped with the cerium 3+ ions. So based on this technology, we can choose the blue LEDs, put it together with a silicon glue yttrium aluminum garnet doped with the cerium 3+ ions, and put some electrical current to this chip and receive the white light. So this scheme in general applied for any purposes. So there are different mono, D, and 3 rare earth doped phosphors. It looks like a very complex chemical mixtures. You can see on the slide a huge amount of formulas, yes, and finally some semicolons, and it means that doped with some rare earth elements like a cerium 3+, europium 2+, or maybe 3+. It's also can be used for red emission especially, and all of them used for conversion blue emission of semiconductor, for example, gallium nitride semiconductor materials to the white light. In the past 10 years, the most spreadable phosphor are silicate, aluminates, nitride, and other ones. Practically, the large photoluminescence intensity phosphors can be changed in the morphology phosphor or maybe change the activator. So both of this approach used for prepared maybe the new powders, which allowed us to change the color, maybe spectrum, suitable spectrum to, for example, if we speak about the plant, to absorption and realize it more effectively, as much as possible, of course. So the future aspect of change in the morphological properties of the chemical engineering rare earth phosphors have been also proposed, because it's really difficult question. There are a lot of scientist group nowadays working in this task, but it's not so easy. But I think that it looks like the challenge. So also the various conventional electrical lamps used for horticulture lighting have the capacity to boost the quality and quantitative yield of the plants. So they all suffer from certain limitation. The first one, energy conservation, is one of the major concern in the controlled environment agriculture that utilize conventional lamp. So especially in the northern latitudes. New generation LEDs, luminaires, have emerged as a potentially available and promising plant lighting system. It can be used in controlled environment agriculture. So emergence of solid state lighting has not only offers the energy efficient interior agriculture, but has also opened up new frontiers for studying plant response to specific wavelengths and or maybe radiation quality. A detailed comparison of the attributes of LEDs and conventional lamps used for plant lighting is essential for comprehensively assessing in the benefits of using LED in indoor cultivation setups and plant research, of course, plant research laboratories. So to conclude this part, I would like to discuss that we have practically maybe several lamps, we call them light sources, which used for growing, yes, for the plant growing. Practically more often used in the horticulture nowadays, of course. Application, the sodium, maybe fluorescent lamps and LEDs with different color combinations. Today, the application of LEDs as the source of main or supplementary light has gradually revolutionized artificial light culture of plant growing in the protected ground, one of the most difficult technologies of modern agriculture. So, as usual, LED can successfully replace incandescent lamps and control light-dependent effects in plants. So they are also a competitive alternative to, for example, gas discharge lamp, like a fluorescent lamp or maybe high-pressure sodium lamp. So in the next part of my presentation, I will give you some recent examples. So about how LEDs with different colors, with different photon flux density can be used for plants illuminations. I would like to consider some examples connected with the first about the Chinese cabbages as a plant. So recently, information about influence tunable spectrum on the plant growth was published in a paper in the Life Science and Space Research Journal. So in this paper, the authors describe the approach for tunable LED lights for Chinese cabbage growth. Authors use the spectrum resemblance. So this approach, it looks like just imitate, yes, to evaluate spectrum resemblance of the as a prepared LED lights. So first of all, the scientists measured the absorption spectra of the Chinese cabbages. You can see it on the slide. The absorption spectra of the cabbages consist of the two peaks. The first peak located in the blue region. The second one is located in red region. Especially the maximum of this band is 680 nanometers. The blue light of 400 to 500 nanometers is important for chloroplast development. The red light with a peaking at 600 nanometers affect the plant morphogenesis and develops the photosynthetic apparatus by regulating the synthesis of photochemicals. A Wiley centered at 500 nanometers indicates that there are several weak absorption bands in this one. So it implies for scientists to think how they can improve the colors for increase the morphogenesis process. So how we can use it and how we can make it. So LEDs with the various spectra were fabricated by combining blue chip and different phosphors based on the aluminum, fluoride, and aluminum garnet phosphor doped with the cerium 3+ ions. The blue chip was the first fixed on the bottom of the reflector. Then the phosphor were used in investigations mixed with the silicon fully, and the obtained phosphor silicon mixture was coated on the surface on the LEDs. Then the LED were assembled on the aluminum substrate and added concave lens to produce different lights. So here is some spectra of the as prepared LEDs by combining blue chip and complex phosphor. So what they are received using this approach, resemblance of the LEDs. So as you can see, that the different LED treatments have the same trend. The order to the fresh and dry weight was estimated. So the root-shoot ratio has been introduced, and it also the greatest parameters. As you can see on the slide, the different emission of LED lights with a different phosphor composition really directed to the some morphogenesis of this plant. So you can see that more better if we use BSRY, it means that blue, sharp red, and yellow, and also blue, broad red, and some yellow, blue, broad red, and more yellow, light treatment than others. It's more effective. If we can see on the red parts of the these plants, you can see that it's not so high in comparison with another one. So another example of LEDs application was investigated for lettuce. So until today, fluorescent lamp is used as supplementary lighting for plant growth, as I said previously. However, fluorescent light does not fit so well with the absorption of plants. So plant pigments have specific wavelength absorption patterns known as absorption spectra. So here is the absorption spectra of lettuce, and also consists of the two peaks located in the blue region and red region, and also connected with the chlorophyll A, B, and carotene absorption. So sunlight in general, our natural light source, covering the visible region, and you can see it on the slide that it's the best color rendering from human eyes. And the yellow light may slow down the plant growth. Unlike sunlight, the spectrum of fluorescent light as a typical artificial light is a discrete, lack of red component, and excessive yellow light. Nonetheless, in the green-yellow light region, there are several weak absorption bands which could act synergetically. Therefore, the author assumed that the ideal light for the growth of lettuce should have an emission spectrum to overlap or contain in the absorption spectrum of lettuce. In light of color rendering for humans, the suitable light for the growth of plants as light with a good color rendering was defined. To verify the hypothesis, the LED light with the various colors were fabricated by combining blue chip and complex phosphor. And also this approach was used, but not only the, especially for another plants, because you can see that some a little bit difference, but in general we have some effects. So you can see that red, yellow, and blue light is distinctly similar to the ideal spectrum, which may be the light with a good color rendering for the growth of plant. So you can see on the slide that lettuce plants under as prepared light treatments show the more effectively way. So based on this result, the radiation use the red, yellow, and blue light, the leaf area growth rates and dry weight of lettuce is about 3 times as high as that under the radiation of, for example, if we speak about SRB light, respectively. So the lettuce grow faster under BRB light comparison with the SRB, but faster under near white light than broad white. Narrow white is a little bit faster comparison with the broad white emission. So these findings show us a promising way to presume the optimized LED light for plant growing. Of course, another side of this part can be considered if we speak about the important characteristic of the LED, like illumination mode. So connected with a PPFD, photosynthetic photon flux density. Previously, I briefly introduced it. What is it? So this parameter directly influences on the spectral composition of radiation and the mode of illumination. So as usual, we don't know which PPFD is more suitable for the plant, but these parameters depend on the type of plant, planting density, growth condition, and on the specific cultivation target. In our published work together with the Chinese scientists in the Lighting Research Technology journal was focused on how different levels of PPFD influence on the plant growth. The aim of the present work is to determine the optimal level of LED radiation for wheat seedings using various parameters of morphogenesis. So we choose the soft wheat as a model plant. So the light flux was provided by specialized irradiation unit, which allowed us for manipulate the LED's emission, I mean that PPFD, and the spectrum was constantly, doesn't change. So control system for the phytotron, we call this installation as a phytotron, was developed for the technical implementation of automatic lighting. The photo period of our experiments was fixed and consists of 16 hours. The adjustment of irradiation modes was carried out by changing the current in the LEDs, I mean the electrical current. So what we have found? We found that the optimal PPFD with the continuous spectrum. So here is the spectrum of the LED which was used for our experiments. Located in the range from 82 to 100 micromole per square meter and second. This will make it possible to reduce the radiation in the early stages of development without harm to the plants, which will reduce the energy consumption required for their cultivation. So, to conclude, I would like to say that LED is a kind of sustainable lighting and ideal alternative for plant growth. So, using LED, we can directly convert electrical energy into light energy. According to the latest report, LED has a remarkable energy-saving effect. The electro-optical conversion efficiency can reach up to about 60%. So, as usual, LED can be powered by flexible direct current power supply. So, it's really important However, we can use in this case the fluorescent lamp, but the fluorescent lamp in general use alternative current. Maybe it's okay, but sometimes it's not so good. Also, LED can easily realize intelligent control of light quality, intensity, and photo period, which is very difficult to realize for legacy light sources because it's most important thing. Due to its optical characteristic and spectral advantages, LED light source cannot be matched by a legacy source in plant production. So, in conclusion, I would like to say that application of artificial lighting as a supplemental and solid light sources for growing plants has been in practice for almost a century. Advancement in lighting technology have allowed the implementation of electrical lamps at large scales for controlled environment agriculture. Conventionally, filament, for example, or maybe gas discharge electrical lamps, maybe some different high-intensity discharge lamp, also have been employed in greenhouses and controlled environment plant production units. But high power requirement and relatively short lifespan of this lamp made such crop production system highly uneconomical. Furthermore, the lack of intelligent control and risk in handling and disposal reduce the usefulness of incandescent lamp or maybe gas discharge lamp for large-scale interior agriculture. So, in general, the most trend to development of power-efficient high-brightness LED has been a major breakthrough. So, the scenario may be changed if we will use some maybe not the blue LED chips, but maybe blue laser LED chips that increase the efficiency of the emitting phosphorus, especially as a converter, and receive more light, which may be more helpful for the plants. Today, LEDs have the ability to deliver photons more precisely than other contemporary electrical lamps. For in general, LED have been recognized as a new artificial light source to promote photosynthesis, to regulate photomorphogenesis, and to enhance nutritional quality of leafy vegetables due to several aforesaid advantages. Advancement in LED technology over time, including packaging, in general current drop, phosphor coating, intelligent control, artificial intelligent, and also can be play a vital role in this case. So it means that LED can be smarter. Now it's also the smarter for question connected with the plant production system. Finally, as a closing points, I would like to say that we discuss the main principle of operation of the most usable light sources based on different physical phenomena. Today is not exist ideal light sources which can be applied for the plant cultivation and the plant growth. In this case, it's really important to select a light sources with a suitable spectrum, efficacy, and reliability. So, at the end of my presentation, here is the references which I have used for preparation to this speech. I express my gratitude to School of Advanced Manufacturing Technology, our research group, and Chongqing University of Science and Arts for fruitful collaboration in the phosphorus topics. So thank you for your attention. If you have some questions, I will be glad to answer on them. Please don't be shy and write it in the chat, and I will try to answer of your response or your feedback for next discussion of our lecture. So as you can see, there are a lot of artificial light sources can be applied in this this topic, but if we speak, for example, about the advantages, I said, but if we speak about the disadvantages of LEDs, so in general, the limitation of more spreadable application of LEDs is the price. So a little bit higher price comparison with other legacy lamps is not stop more spreadable application, the LEDs in this sphere. But I hope in nearest future the situation will be changed, and more indoor and outdoor lighting application will be constructed using the LEDs. So there are a lot of possibilities in this case, especially connected with the material science, because the material science plays a vital role in this case. As you can see from the presentations, there are a lot of phosphors, really efficient phosphors, and there are a lot of investigations in this case. There are a lot of papers, some projects can be generated in this sphere. So I hope that this question connected with LEDs will be constantly improvement for the questions connected to the plant growth. So the price may be the first limitations, I think, but the next one is self-thermal igniters. So it means that thermal drawbacks, because when the LED works, I mean that high efficiency LED. So it means that the light dramatically decrease, especially when we put the phosphor in a silicon compound and put it into blue chips. We during the time the degradation process is occurs. So recently there are several approaches to solve this problem, like for example using some ceramic materials or maybe glass ceramics materials, because this type of materials in generally dramatically increase the thermal resistance of this type of materials, and it's really helpful to increase the lifespan of this composition, because you see that the lifespan in general of the LEDs is really huge, more than 30,000 hours or more. It depends on the company which was produced this type of LEDs, but in general, these LEDs work practically maybe not higher than this period of time, but it directly connected with the materials which is used for transformation electricity into the light, into the visible light, especially the warm color light or maybe cool light for lighting and maybe for illumination. It doesn't matter, but in general it's happening. So questions, please, questions. If you have some questions, I will be glad to answer on them. It will be shine. So I will try to translate. There's some questions in the chat because it's in the Russian languages. So good afternoon. The emission of the sun, 0.5 level of the maximum threshold intensity. The main role in this one occurs the infrared region, especially the spectral region from the 750 nanometers to 1 micrometers. Just only incandescent lamp emit in this spectral region. So do you know so which on which properties on the plants influence the absence of infrared radiation? So yeah, in general, it's a quite interesting question, because our natural light is really optimistic, yeah, for the for the plant growing. But the drawbacks of incandescent lamp in general, more maybe it's not suitable due to some disadvantages, like for example, um, not efficiency light sources, yes, but sometimes we can use maybe some in general we can use some semiconductor emission. Practically, scientists used it some additional heater or maybe some other radiation like LEDs with increasable spectrum, red emitter spectrum in the red part of the spectrum. So this combination in practical influence on this on the plant, but as usual, the plants can be red light. I mean that influence on the flowering process in general. So of course we have not only the flowering plants, but in general it can be used and can be applied for to increasing the productivity of light. Here is some information about the different colors and its influence on the emission of radiation, because it's really interesting and there are investigations connected with this one. So, but unfortunately, maybe, as I said, we have not some ideal recipe, yes, to increasing the productivity of plant growth. But why not? Because the technologies is constantly increases, and especially in LEDs, and using some several approaches like using the different phosphors for illumination the plants, we can significantly increase the productivity of the plants. But in general, there are a lot of attempts in this one. So I have shown for you practically 3 of them. But if you try to focus on this question more in detail, you find there are a lot of investigations in this one. Because, yeah, light, it's not that more maybe favorable, yes, more maybe vital. Of course, it's vital, but in this case, we should to focus on another type of parameters like water, like some vital compositions, some heat, and some environmental, some wind, and also on. All of them in the complex, the influence on the growth of light on the plants in general. So, but light is maybe just some, it looks like the starter of the process. Yes, if we will try to grow the plants without some lighting, we of course the light will play a vital role. But if we turn off the light, we will change some process which activate the photochemical reactions. And as I said previously, and I showed previously, we did not find so many colors of the plants and so on, because it's really important in anything. So infrared emission, yes, but unfortunately, the sun, we have artificial infrared radiators, especially the monochromatic radiators, but just only narrow band emission, but maybe not so suitable for the absorption band. Here is, I show you some examples of the absorption spectrum of the cabbages or maybe lettuce and something like that. I hope that I answer it on your question. Biological system, it's really difficult, really complex for investigations, but for food production, it's really important. So it means that we can produce the plants without some sunlight. Yes, so we can use some, for example, some boxes. I mean that some boxes without some any windows, which that influence on the emission from the sun. Just only use the artificial lights. Of course, there are a lot of questions connected. How these plants influence on the us, yes, on the peoples, because these investigations maybe just only started, maybe more spreadable. I mean, like the hot topic, maybe recently, several years ago. But in general, it's also really interesting how the light influence on the plant, and how the plant influence on the us, yes, as a produced and the growth using the artificial lights. So it's really difficult questions. I think that nobody knows, because it's maybe the frontiers investigations in this topic. So just only one question. So please don't hesitate. Because we have several minutes for discussion, it will be vital to discuss with you. Maybe you will have some new ideas about this one, because you know that it's really huge topic. There are a lot of scientific groups work in this direction, and especially for me, maybe I don't know maybe a lot of things. Yes, I just can share with you only small piece of information. You know that all of this lamp is really huge amount of literature, some experiments and so on, because it connected with the lighting characteristics, it connected with the materials. There are a lot of scientific groups. The combination of these groups work under these light sources. Of course, in general and maybe traditionally, this type of light sources is used for general lighting, yes, for on the street or maybe in indoor, outdoor, but scientists try to use it for this special question, like horticulture applications. It's really important, I hope. These topics, it's really development in different countries. So please don't hesitate. Give me your feedback about the information connected with my short presentation. So just keep a silence, okay, if you have not any questions. So thank you so much for your attention, for your participation. I hope that together we save the planet, yes, and I wish you good luck if you focus on this really difficult question as an application of artificial light for horticulture. Thank you so much again for your invitation. See you next time.